we've already confirmed that that's on its way, so we're happy everything's going well so far.
Now, Stuart, I understand we have animation to show folks that will help them go through the paces and see exactly what's going on.
Right. Go ahead and show the animation. I'm not sure I have it here in front of me, but what we're seeing is first we're oriented towards the sun and towards the Earth, which is why the main antenna at the top is illuminated, but then we're turning to an attitude that puts us so that the main engine on the bottom end of the spacecraft can burn to slower velocity and put us into orbit at the right time. We also, before we do the burn, we fire our thrusters to slow ourselves down as we're rotating. Then we perform the burn. It lasts for about 35 minutes. Once it's over, we fire our thrusters again to get us back into 2 RPM, 2 revolutions per minute, and then we go back to the regular attitude.
So that is what is going to take place later tonight. Now let's check in with Tracy Drain at Lockheed Martin. Tracy, can you explain to folks why we have 2 mission support areas here?
Yes, I can. People might think it's a little bit weird that we have 2 MSAs, but JPL worked very closely with Lockheed Martin in developing the Juno mission. JPL manages the mission, and we do key roles like mission management and navigation from there. Lockheed Martin built the spacecraft and pre-launched during a period called ATLO, which is assembly, test, launch operations. All of those huge pieces of equipment you'll see later tonight about Juno spacecraft came together. The vaults, the electronics vault that you'll be hearing more about, the large solar arrays, they were all assembled here and then put through a battery of environmental tests to make sure the spacecraft would be able to handle everything it's going to see in cruise, and once we get to Jupiter, getting into orbit and going through all of our science phase. So if you were to look around the MSA here, you'll see that the subsystem experts are located here at Lockheed Martin, from thermal, power, fault protection, flight software, telecom, GNC. We're going to be talking to a couple of those subsystem engineers later tonight. We like to have 2 fully staffed mission support areas because if you have some kind of connectivity issue either at JPL or here at Lockheed Martin, we'll still be able to monitor the spacecraft from either location. We actually sent a couple of JPL engineers out here to Lockheed Martin, myself, a tones engineer and a navigation engineer, and several engineers from Lockheed Martin to JPL, those that are most critical in our Jupiter orbit insertion events, like propulsion, guidance, navigation and control, a systems engineer, and an ace. And what you'll notice if you look around, everyone's wearing the same color shirt. That is kind of one of the reasons you can see that we're all one team, all working together. If both MSAs stay up, we'll both be in communication with each other, following along as our vehicle goes through this huge event to get captured into orbit around Jupiter.
All right. Thanks, Tracy. Okay, the key times tonight to focus on are the start of the main engine burn. That'll be about 8:18 p.m. Pacific time, 11:18 Eastern. And then the end of the burn, about 35 minutes later. That's around 8:53 Pacific, 11:53 Eastern. All of these times are Earth-received times. A timeline of these spacecraft events will be on display throughout the show. However, these are mission-projected times. The actual times could vary when executed by the spacecraft. And some other info that could come in handy tonight. If you have to leave home to go to a barbecue or see fireworks tonight, no worries. You can continue watching on your mobile device. You'll find the links by going to twitter.com/NASA Juno or facebook.com/NASA Juno. And please feel free to ask questions by using hashtag Ask NASA. Now let's go back to Stuart to get an update. I understand the spacecraft should be swapping antennas soon. Is that right?
That's right. We're expecting to go from the main antenna that you saw at the top of the spacecraft. It's actually the medium gain antenna located at the top next to the main antenna, to a different antenna at the end of this turn. When we get to the end of the turn, we'll be oriented in such a way that we'll need to use a different antenna on the spacecraft. We started out pointed towards the Earth like this, using the main antenna, and then we swapped to the medium gain antenna located nearby. We're performing this turn now to go to an attitude that's more like this, and we're going to perform that burn very close to Jupiter, where you see here, very close to the cloud tops. And we're going to use an antenna at the bottom of the spacecraft to do that. It'll be pointed towards the Earth, but we'll get a very low data rate out of it. And we'll be able to get something we call tones that tell us when events have transpired and know what's going on that way. We'll also get another type of signal called Doppler from the main radio transmission from the spacecraft, which I'll tell you more about later.
Stuart, can you explain to us why it's necessary to swap antennas and what's the difference between these two antennas?
Sure. The main antenna at the top, the high gain antenna, or even the medium gain antenna that we were using a short while ago, they allow us to get a larger data rate and to transmit telemetry, in other words, to get more detailed information down from the spacecraft. It's more like using your flashlight, for example, to illuminate a wall, and you get a very narrow beam, and it's a high gain in that sense. What we're doing in the case of this lower gain antenna that we're about to swap to is to use something more like a light bulb that lets us illuminate all around 360 degrees and transmit less light at any given location. And because of that, we can still get a signal, but we do it with a very low signal strength, and we get these tones that tell us only that a certain milestone has passed. So it's useful information, but it's less than our regular information.
So if I have this correct, the fact that you're on a low gain antenna means that you have less information, less data, so you won't be able to know a lot about the spacecraft, just that it did what you wanted it to do?
That's right. We'll be able to tell that, for example, a turn started or a turn ended, that we were able to start damping the nutation or the wobble of the spacecraft that occurs naturally after a turn when we're doing that with a spinning spacecraft. And when that nutation damping ends, we're also going to do a spin up that I told you about in the video and a spin down that will be indicated by tones. And when the burn starts, we'll get a tone. Now, we won't get any tones if everything goes well until the very end of the burn, but then we'll get a tone at that end, at that time as well.
So I understand that the antenna swap is going to happen any time now, so we're going to stand by and listen to the MSA.
That's right, and I believe we just heard that tone announced on our broadcast here in the mission support area for the swap to the toroidal low gain antenna. It was actually a tone that we weren't sure we would receive because it's happening in the middle of this large turn that I was telling you about, but we did in fact receive it. And so we know that not only have we swapped, but we're in the middle of that turn, and we're continuing to get this other signal called Doppler that we'll tell you more about a little later.
All right, and let's talk about how we receive that information.
Mm-hmm.
We receive it through the antenna, through the Deep Space Network. Which of the stations will be listening this time out of all the different stations of the Deep Space Network?
Sure. We have to send that signal from the antenna on the spacecraft to an antenna on the ground, of course. And so we use antennas located all around the Earth. We space them evenly around the Earth, and we call this the Deep Space Network. Currently, we're receiving the signal at stations in the California desert
We see the tone
called
indicating
Goldstone.
the transition to
We're
idle
actually
mode
using
and
multiple
nutation damping.
antennas to receive that signal. And so we receive the signal at 5 different stations in order to boost the signal and make sure that we get the tones, and also for some redundancy. Now, a little later, we'll also be getting signal at Canberra. In fact, I think we are doing that already. We're overlapping with the Canberra station, and that's in Australia, so that both Australia and the California desert can see Juno on their sky right now.
All right. While you were telling that, Stuart, we did hear a call on the VOCA. Do you know what that call was?
I believe that was for nutation damping, which follows the end of the turn. So we got two tones, actually, one for the guidance, navigation, and control mode to idle, which signals the end of the precession or turn that we were involved in. And then another one for the start of the nutation damping, the wobble damping, that occurs afterwards. We're performing a big turn on a spinning spacecraft, so there's naturally a little bit of wobble that occurs after that, and we're actively damping that with our thrusters. We'll get another tone in a couple minutes that will signal the end of the nutation damping.
So we're basically getting into position then.
Right. Everything so far has been happening pretty much right on schedule. We couldn't be happier with it,
On
the
Juno
progress
and
of things so
nutation
far.
damping has completed, and we see the tone for the 3-pulse precession.
So it sounds like the precession is complete and damping is complete and we're in position. Is that right?
That's right. We just get that tone, and in fact, we get another tone indicating another precession or turn that's actually a cleanup turn, 3-pulse precession.
Excellent.
That will put us into even better position for the JOI burn.
Oh, that's excellent. Thanks, Stuart.
Sure, no problem.
Well, Juno's instruments and camera were turned off 5 days ago to protect them during this maneuver. That means there will be no new pictures tonight. But we do have an interactive visualization that you can load onto your computer and virtually ride along with the Juno spacecraft as it arrives at Jupiter. Now, this computer simulation uses the mission's predicted data. It's called Eyes on the Solar System. Kevin Hussey is the manager of the JPL Visualization Technology Applications and Development Group, and he's going to demonstrate. Kevin?
Thank you, Gay. The first thing you need to do is find the application and install it. So this video is going to show you how to do that. Okay, please note that this software runs on Windows and Macintosh operating system computers. Now, we're going to go ahead and hit the Explore button. I'm going to take you quickly and introduce this module to you. This is Eyes on Juno, if you will, and it's a real-time interactive view kind of over the shoulder of the spacecraft, looking at whatever it is you choose to look at. For example, all I need to do is click and drag, and I can spin around the spacecraft. And in any of our Eyes products, anything with a label has, you can click on it and you can fly there. So I'm finding Io at the bottom of the screen. I'm going to double click on Io. Now we are at Jupiter's moon Io, and we'll be looking back at Jupiter there shortly. You can see Juno coming over the North Pole. So these are a couple of Eyes basics. Along the top, you have the different chapters in the software. For example, right now we're on the home screen. You can go to the mission screen. You can go to Juno Orbit insertion, as well as a science chapter and one about the spacecraft. But I've already got a lot of mail about controls. For example, can we show the units in the metric system? Yes, you can. You go to the control panel and you click on the ruler and it will toggle between the metric system and imperial. Let's take a look at the mission module. So when we click on this, we are able to look at the different either mission phases or mission events. Let's take a look at a mission event. The Earth flyby, you can see it's on the list here. So if I click Earth flyby, I'm going to be able to see this from two perspectives. In the picture-in-picture, you're going to see a view over the shoulder of Juno, seeing how the Earth would appear. And in the screen to the left, I'm scrolling in, and you can watch Jupiter as it slingshots past the Earth and heads out toward Jupiter. Now, if you look down at the bottom left of the screen, you have the time. This was October 9th, 2013. All right, so you get an idea. You can go back in time. You can go forward in time. I'm going to move us now to the time or the chapter about Juno orbit insertion. And what I'm going to do is I'm going to click home, and then I'm going to click Juno orbit insertion. And now we have special features here that allow you to do several things. You can turn on artistic renditions of scientific model output. For example, here's a model of the radiation fields at Jupiter. I'm going to turn on the aurora and turn on its magnetic field. Again, these are just visualizations of a scientific model, and you can turn those on and off at will. I'm going to clear those, and I'm going to show you what it would look like if we swung around and looked at this from the perspective of Io once again. So I'm looking for Io. There it is in the field of view. I click on it, take you to Io. I'll look back at Jupiter. I'll close this. And as you'll be able to see, there's there's Juno coming over the north pole of Jupiter as we stand now. So these are just a couple of the things you can do with the Eyes on the Solar System Juno module. We hope that you will try this at home. It's rather simple, and it allows you to do what you'd like to do within the context of the Jovian system. Thank you very much.
All right. Thanks, Kevin. We are also using Eyes in our coverage tonight, and just like us, you can use this module dedicated to Juno on your own computer by going to eyes.nasa.gov.
Some data. Could you check on that?
And let's check back with Stuart right now to see what's going on.
Sure, Gay, it sounds like we already received our tone for the start of the spin-up to 5 revolutions per minute. This is the spin-up that I was telling you about earlier that takes us from 2 revolutions per minute, our normal spin rate, to 5 RPM, which is what we're going to use to be a little bit more stable for our JOI burn. So we're already in the right attitude. Now we're going to spin up to 5 RPM and be at the right spin rate. And then there's just a couple of other little things to do before we start the burn. So everything is looking good. There's some time variability naturally built into the sequence of events on the spacecraft, and these things happened pretty much as we expected within that amount of variability we were seeing.
We have some animation of the spin-up. Can you explain why it's so necessary to increase the spin rate?
Sure. If you look at the thrusters that are burning right now, they're causing the spin rate to increase from 2 RPM to 5 RPM. Basically what you get is it's like a bicycle wheel. The faster you spin it, the more stable it is. So for a large spinning spacecraft with a lot of mass at the end of the arrays and also in the solar arrays themselves, it's just more stable when we're at 5 revolutions per minute. And when we're going to do this burn that wobbles us just a little bit, it'll help to keep us stable and on the right attitude, the right pointing during the burn and by the end of the burn.
And when you're firing the engine, you need it to be more stable, I imagine, then.
A little bit, yeah, and it helps if we weren't exactly at 5 RPM, we'd still be okay, but we are confident from what we heard that we started the spin up to 5 RPM, and shortly we'll be getting a tone that tells us we're at the end of that spin up.
All right, so we'll be standing by.
Systems, this is Nav.
Go ahead, Nav.
Yeah, we see the expected change in amplitude as the spacecraft spinning up and the Doppler residuals.
Copy that. All stations on Juno Court. At this time, we see the tone for idle mode, indicating the spin is complete.
All right, we hear that the spin-up is complete. Can you explain what that means, Stuart?
Sure. Like I was telling you a minute ago, what we got is a tone that tells us
Go
that
ahead
the spin up from 2 RPM to 5 RPM has ended. And we're seeing that reflected in another signal that we have also called the Doppler. And I can tell you a little bit more about that if you like.
Good news. Thanks for the confirmation.
We hear a
And
confirmation.
at this time, we do expect no further tones until 2 minutes before the burn begins.
All right, so we will not be getting any more tones until 2 minutes before the burn begins. Well, joining us now is Richard Cook. He is JPL's Acting Director of Solar System Exploration. And as we mentioned earlier in the news conferences, big concern is the radiation, dust, particles. All these things could be fatal for the spacecraft. This sounds like an extremely risky endeavor here.
That's right. I mean, Jupiter is the king of the planets, and it's certainly the most dangerous environment that we will send a spacecraft into. It has very high radiation, strong magnetic field, and so the spacecraft is really now entering the phase or the part of its voyage that we worry about the most.
As I understand, I mean, the team has prepared as much as it possibly can, but the thing that they can't anticipate is whatever Jupiter throws at them.
That's right. Although there are some things that we have done in terms of the design of the spacecraft. In particular, because it's so far away, we really can't joystick it. We can't control it, directly. We have to basically program it ahead of time to tell it what to do. And so a lot of what you're hearing is the spacecraft essentially doing exactly what we told it. That's a good thing. In addition to that, though, we provide protection in software so that if something goes wrong and the spacecraft, for example, the computer resets because it gets hit by a piece of radiation, it will restart the sequence of events. And so once the burn starts, actually all of the activities that it's doing now, if for some reason it gets interrupted, it will retry, and it will keep retrying that until it finishes it.
And how would that affect things if that should occur today? If it gets hit by radiation or a dust particle and it decides to stop down, it'll just restart?
It will. It'll take a little time. Depends on what happens exactly, but usually the software restarts just like on your home computer. When something goes wrong, you start it up again, and it takes a little while to get going again.
So it's a reboot?
That's right. And then it
Okay.
figures out where it is and starts up again after a little bit of time. And so it may delay things,
Okay.
but it'll still occur in time to get us in orbit around Jupiter.
And so much of what we're doing tonight is keeping an eye on the timeline and seeing that things occur at a particular time. If there is a reboot, what would happen in terms of our timeline?
Depending on which scenario it is, it could be anywhere from just a few seconds to more like 10 minutes, where it would, by the time it comes back up, once it's firing the engines, if it is interrupted at that point, it basically waits for about 8.5 minutes, and then it starts up again and tries to continue burning the main engine.
So if we see a change in timing, the team's not worried?
No. I mean, it's as I said, we are worried about this particular phase of the mission, and so we build in all these protections that allow us to recover from problems.
All right. So it looks like so far.
So far, it's going great. Very excited about what we're seeing.
All right. Thank you, Richard Cook.
You're welcome.
And this is live coverage of Juno's arrival at Jupiter on NASA TV and the web. Tonight is what they call a critical event because it's a do or die moment. If the spacecraft is not safely placed into orbit around Jupiter, the mission is lost. And for those of you just joining us, here's a look at what this spacecraft is about to encounter.
The scariest thing to me about Juno are the unknowns. So much about the environment that we'll have to withstand is unknown. Nothing's really certain about what's going to happen.
It's a monster. It's unforgiving. It's relentless. It's spinning around so fast, its gravity is like a giant slingshot, slinging rocks, dust, electrons with whole comets, anything that gets close to it becomes its weapon. It just so happens, deep inside this body are the secrets we're after. Secrets about our early solar system.
It's the biggest and baddest planet in the solar system, and it's got the biggest and baddest radiation and the biggest and baddest magnetic field.
The background radiation that we're exposed to on Earth is about a third of a rad. What we expect to see at Jupiter is about 20 million rad. No spacecraft has ever flown this close to Jupiter, flown this deep into the radiation belts.
So the real trick is, we gotta go in close, get the data, and get out. And the first time we go in, that's the most dangerous. We call it Jupiter Orbit insertion. J-O-I.
Nothing's really certain about what's going to happen.
And it's a minute past the hour. We are not too far off from the start of the main engine burn. That takes place at 8:18 Pacific time. The engine will burn for 35 minutes to slow the spacecraft by about 1,200 miles per hour, 540 meters per second. So it can be captured into the desired orbit, which is a 53-day orbit around Jupiter. Right now, let's check in with Tracy Drain with the team at Lockheed Martin. Tracy, how is the spacecraft doing over there?
Hi, Gay. The spacecraft is doing just great. We recently heard that we got spun up to 5 revolutions per minute, just as we expected. And right now I'm here with Kristen Francis, who is our guidance, navigation, and control lead out here on the team in Lockheed Martin. So, Kristen, why don't you tell us a little bit about what a guidance, navigation, and control engineer does on a mission like Juno?
Sure. So as a guidance, navigation, and control engineer, I'm primarily focused with attitude determination and attitude control. By attitude determination, I just mean where the spacecraft is pointed in space and how it knows where it's pointed. So unlike here on Earth, where we have a compass or GPS to know where we're headed, you don't have those things in space. So a spacecraft like Juno has to use the stars in order to navigate. Just like many of the early explorers, like Columbus or Magellan, used the stars to navigate at sea. That's how Juno navigates in space.
Which is pretty cool. It's kind of like old meets new in our space age, right?
Exactly.
So that was attitude determination. What about attitude control?
So attitude control is our ability to change or maintain the spacecraft's pointing, spin rate, or velocity. So for very small changes like turning the spacecraft or changing its spin rate, like we saw it just do, we turned to the burn attitude and we spun up to 5 RPM. For those types of changes, we use very small thrusters that are located around the vehicle. We have 12 of them, and that's what we use to make small changes. For very large changes, like the giant burn that we're about to do to get us captured into Jupiter orbit, we use a very large rocket engine that's located on the aft end of the spacecraft, and that's what's going to give us the big change in velocity that we need to slow down.
That's right. That's our business end of the spacecraft, which is going to see a lot of work tonight. So we've also talked about the fact that the spacecraft is spin stabilized. Do you want to describe a little bit what exactly that means?
Sure. So just like you would apply a spiral to a football to make it fly in a straight path through space, we apply a spin to the Juno spacecraft to make it maintain its pointing, so it can be very stable as it flies through space at great speeds and at very large velocities.
Gotcha. Okay. And so there are obviously some advantages to being a spin-stabilized spacecraft. Do you want to describe some of those for the audience?
Sure. There's several advantages to having a spinning spacecraft, the biggest of which is you're actually using physics to your advantage. So you're using the natural dynamics of the spacecraft to maintain your stability, so any forces acting on the spacecraft can't disturb your pointing. And so a lot of spacecraft are not spin stabilized, and the way they resist those outside forces is they use devices called reaction wheels. But the problem with reaction wheels is they consume power and they have mass. And so being so power conscious, being a solar-powered spacecraft way out at Jupiter, we can't afford that kind of power consumption. And also, by not having reaction wheels and saving that mass, we can put more science payload on the spacecraft.
Which is exactly why we're going to Jupiter in the first place. So it's great that we were able to make that kind of trade. So speaking of science instruments, right, Juno, the spacecraft, is spinning, and some people might be a little bit confused about what that means, about how the instruments are able to see the planet. So can you describe how that works?
So the instruments are mounted on the spacecraft body looking out into the spin plane. So as Juno rotates at 2 rotations per minute when we're in our science phase, each of the instruments can scan their cameras and their sensors across Jupiter at 2 times every minute for the entire time we're closest to the planet. So it really helps maximize our science return.
Great. All right. So this was Kristen telling you a lot about the guidance, navigation, and control aspects of our spacecraft. So we're going to let her get back to her console and continue monitoring the vehicle and hand it back to you, okay?
All right. Thanks, Kristen. Thanks, Tracy. NASA's Juno is about to come face to face with the most massive and perhaps most treacherous planet in the solar system. Scientists have wanted to go there for decades, if not centuries. And here's why. Out of all the planets in the solar system, this team picked Jupiter.
Jupiter's by far the largest planet in the solar system. It has an influence on everything else. So if we want to understand how do planets form, how do solar systems form, we really have to start with Jupiter.
By studying Jupiter, you're going to get one piece of the puzzle, not necessarily how life formed, but maybe how the ingredients that made up life eventually got spread around in the early solar system and got to us.
We care about the light elements because that's what we're made out of. And we've got a puzzle about where these volatile elements, these lightweight elements like nitrogen, carbon, noble gases, where they came from.
To determine how much water is in Jupiter is essential to understand how this planet came to form and then how it influenced the formation of all the other planets in the system.
When the Earth formed, in the absence of Jupiter, it probably would have gathered very little water and organic molecules, which would have been concentrated in the colder outer part of the solar system. What Jupiter evidently did as it formed was to scatter cold material that contained water ice and organic materials to the inner solar system, where it could be captured by the Earth and the other terrestrial planets.
We learn about the origin of the solar system. We're learning about our own origins. We're learning about how life comes to be, about who we are and what our place is in the universe. It's about knowledge and about humanity's quest to understand. For me, that's why we need to study Jupiter and the solar system and almost everything.
Juno's primary objective will be to study Jupiter's origin, its interior, atmosphere, and magnetosphere. By studying these 4 things, scientists hope to get a picture about the history of the solar system, how planets formed, and maybe even how life began. Steve Levin is the Juno project scientist. He is in the Juno science room where members of the science team and their families have gathered to watch. First thing, Steve, what is the single most important thing Juno is going to measure?
So, in my opinion, the single most important thing Juno's going to measure is how much water is in Jupiter. Because the amount of water in Jupiter teaches us a lot about how Jupiter formed. If Jupiter formed really far from the sun and drifted inward, you'll get a different amount of water than if it formed where it is now. If it formed, as we think is likely, from icy planetesimals, large chunks of water, of ice, that collided together and made a giant planet, then you'll get a lot of water in it. You'll get a different amount of water than if it formed some other way, say directly condensing from the same material that made the sun. So that single number, the global water abundance of Jupiter, will tell us a huge amount about how Jupiter formed and therefore about how solar systems form and about how all the planets in our solar system form and ultimately where do we come from.
Well, obviously, this is all about the science. Are we collecting science now? Are we into our science orbits yet?
So right now, because we're totally focused on firing that main engine and getting into orbit and turning the spacecraft back to the sun, we've turned off everything that's not essential to getting into orbit. That means all of the science instruments were turned off about 4 days ago. And right now in our pass by Jupiter for JOI, we're not going to get pretty much any science information at all. What I'm really looking forward to is 53 days from now, when Juno comes around again in its orbit and comes really close to Jupiter. That time, August 27th, we will have turned off the main engine. We won't be using the main engine at all, and we'll have all of our science instruments on. So that's when we'll get our first really good look at Jupiter from close up and learn how Jupiter is going to surprise us.
We're running some of the animation right now, and the viewers can see there's this huge elliptical orbit. Why is that? Why are we not doing the usual circular orbit we always see with satellites? This is a long zip around orbit. Why is that?
So remember, what we're trying to do here is we're trying to get really close to the planet so that we can get our science. And at the same time, we don't want to spend a lot of time in the radiation belts, and we want to have time to send all the data back to Earth. So our science orbits are 14-day orbits. We come around, we come really close to Jupiter for just a few hours, and then spend 14 days sending the data back, recovering, figuring out what we're doing next, and then doing it again every 14 days. To get into that orbit, we have to fire the main engine, of course, get into our big 53-day orbit, come around, do that science pass I mentioned, another 53-day orbit, and then we'll fire the engine again to put us in that 14-day orbit where we can do all the science.
And Steve, why not just go straight to the 14-day orbit? Why do these two preliminary orbits?
Well, there's a couple of reasons why we want to do the preliminary orbits. Part of it is we don't want to fire the main engine that long. Instead of two half-an-hour burns, an hour-long burn of the main engine would actually take it beyond where we've tested it. It would probably work fine, but we don't like to operate where we haven't tried it before. But the other thing is we really want to get a look at Jupiter before we go into that 14-day pace, where every 14 days we have a flyby and we're really trying to do everything and make it all work, and there's not a lot of time. With 53-day orbits, we get this big, long 53-day orbit from when we first look at Jupiter, August 27th, to when we next come around and put ourselves in the 14-day orbit. That means we have time to look at how all the instruments operated, look at what Jupiter did to surprise us, and make sure that we're set up to get the science as we come around.
So you've given the grace of having a little prep time.
Exactly. We've set up a little time for ourselves to prepare just in case something about Jupiter is different from what we expected.
All right. We mentioned that the room there is full of scientists, and I'm told that some of the scientists in there are quite young.
That's right. So we have with us some of the people who have, obviously, the science team, right? People who've worked on the science for Juno. And we have some members of the Goldstone Apple Valley Radio Telescope project. So we have students all over the United States, and in fact all over the world, who learn about science by doing real science. They operate a radio telescope that belongs to NASA. They operate it remotely, and while they're learning science, they're doing real science. Part of the science they've done is observe Jupiter, and that contributes to the Juno mission, so they're effectively members of our science team. I have one of them with me here today. Renato, if you want to talk a little bit and tell them about Juno, I think that would be a great thing.
Yeah, first of all, we are from Chile, so take the control of the antenna from thousands of kilometers to the south is like a dream for any person who likes the science and the universe.
So when you've observed Jupiter, of course, do you want to tell us just a little bit about how you do that and what kind of observations you do with the telescope?
Yeah. First of all, we connect to the Lewis Center, and then they, like, thanks to some software, we take the control of the antenna, and thanks of that, we collect the I don't know how to say in English, but the information of the antenna and Jupiter.
Thank you very much. So I guess it's back to you, Gay, from the science team room. I think we're all really excited and looking forward to JLI.
Thank you, Steve. All right, we are just a few minutes away, about 4 minutes or so minutes away from the start of the main engine burn. Let's listen in on the team. All right, Stuart, we are just about a minute away from the main engine burn. Can you explain what this is and how critical it is to the team?
Sure. We're waiting for the start of the burn. There's going to be a tone or two that we'll hear just in advance by a minute or two. We'll get a tone or two right at the start of the burn. And this will indicate that the burn is starting, a 35-minute burn that'll put us into orbit in this kind of an attitude, burning in such a way that it slows our velocity. We're moving in the down direction, and so we're going to slow ourselves so that we're not moving as fast, and that will put us into orbit. We're also noticing from our Doppler signal, which you might have seen, that we're doing exactly the things that we expected that we would do. We performed the turn, we performed the spin up, and we're seeing those signals in the Doppler. We'll also see that signal very clearly in the Doppler once the burn starts, so we're waiting for that as well.
Right.
Everything's looking good.
Standing by.
Systems, this is Nav.
Go ahead, Nav.
Yeah, we see the expected sharp shift upward and the Doppler residuals indicating the main engine has started.
Copy that. That's good news. We are still awaiting confirmation of that in the tone.
All right, the main engine burn has started, and that will continue for another 35 minutes. And that's the time they need to put this spacecraft into a 53-day orbit. That is the orbit that they are looking for. And while we wait, let's check in again with Tracy Drain over at Lockheed Martin.
Hello, Gay. Yes, we're all very excited to hear that the burn started on time. That's the whole reason why we're here tonight. So the team is really, really happy about that. But for now, we're going to take a minute, have a little bit of a breather, and have a conversation with Will Santiago, who is our thermal lead on the project. So, Will, why don't you explain to our audience what it is that a thermal engineer does on a mission like Juno?
As the Juno thermal engineer, we're primarily responsible for making sure all the temperatures are within the limits. So we have the electronics in the vault, for example, that want to be operating at room temperature to optimize the performance. At the same time, we have these instruments like GIRM that detects heat. It is looking at the auroras in the infrared spectrum. So it needs to be really cold to make the instrument the most sensitive possible. So we have all these computer models that allow us to predict the temperatures and also the power, the heated power that we use in the spacecraft.
Okay, and so when we talk about JOI, right? There's a lot of challenges associated with JOI. There are also thermal challenges associated with getting into orbit. Can you describe some of those for us?
So during JOI, which is happening right now, of course, we are at the JOI attitude. That means that the solar panels are pointed away from the sun. Right. And that means that the temperatures of the solar panels drop very quickly, and we're seeing temperatures on the order of minus 300 degrees Fahrenheit.
Yeah, colder than anything else here on Earth.
Absolutely. They were designed for that, so the engineers early on in development took that into account into the design. At the same time, JOI itself, we had the main engine burning right now, and that means we're seeing temperatures on the order of 2,000 degrees Fahrenheit, if not more. So JOI itself has all these extreme temperatures environment. It's one of the most unique phases of the mission for us with respect to all the thermal gradients that we see on the spacecraft.
Yeah, that's pretty crazy. And speaking of unique and environments, with our spacecraft going into orbit at Jupiter, we have a unique electronics vaults where we put the electronics to protect them from the environment. There are some thermal challenges associated with that too, right?
Absolutely. The vault itself is relatively small, and we have all these instruments packaged in this really, really tiny space. So we have all these electronics that are generating heat, just like your computer would at home. But there's no fans, there's no air in space, so we had to figure out a way, how do we get rid of the energy? So the vault along the walls have these louvers that are just like window blinds. They open and close based on the temperature. So when the temperature of the vault gets a little bit too warm, the louvers open and expose this radiator panel. It's not a hole, it's just a coating on the vault that allows us to reject the heat out to space. And once the temperature drops back down, there is, the louvers kind of close automatically, and that's how we save heater power, because we use quite a bit of heater power on thermal.
Oh, that's right, yeah. So one of the things that Kristen mentioned earlier is that we don't have reaction wheels. That saves us on power. Thermal is one of the most power-hungry subsystems on board the spacecraft. You guys use what, like half?
We use over half of the power, so it was very important for the design early on to take into account all these considerations to make sure like we were tightly insulated.
Right.
So you see a lot of thermal blankets around it, and we had to apply optical coatings to make sure that we don't reject too much heat into space.
That's right. Now, speaking of all the things we're doing in order to make sure things don't get too hot or don't get too cold on the spacecraft, we have to know for sure all that stuff's going to work before we launch the vehicle and it's on its way through cruise into JOI. So can you talk a little bit about what we did pre-launch in order to ensure the thermal subsystem was going to work?
All right, so the spacecraft was built here at our Lockheed Martin facilities in Denver, Colorado. Once it's all insulated and buttoned up, we actually transport it over to a building next door that has this large thermal chamber. It's called the Space Simulator Lab. Yeah. And we take the spacecraft and we raise it up and we drop it into the chamber. And then we close the chamber and pull all the air out of the chamber, just like the vacuum of space. Yeah. And we start flowing liquid nitrogen along the walls, temperatures on the order of minus 320 degrees Fahrenheit. Yeah. So it's really cold. The chamber also, on the other hand, has lamps to simulate a solar load. And during a 3-week period, we go through hot and cold cycles on the spacecraft. We power all the instruments. We power the spacecraft components to make sure they're operating just like they would in space.
Okay. Now, I know we only have a little bit of time left, so the one thing I thought was cool you mentioned to me is that as our spacecraft is passing by the planet, we can actually sense the heat from the planet. Can you say just a few words about that?
So the Jupiter formation days, it's still hot. It's still cooling off from the days of solar system formation. So as we pass by the planet, we actually can detect temperature increases just because of the heat of Jupiter blasting the spacecraft for a short duration of time, but we see a little bit of heat pulse in the telemetry, and we expect to see that during JOI.
That's pretty cool. So We're going to let Will head back to his console and continue keeping an eye on the tones as they come in and pass it back to you, Gay.
Thanks, Tracy. Thanks, Will. And it's about 24 minutes past the hour. We're less than a half hour away from the end of the main engine burn. Mission Juno is a partnership. JPL manages the mission for Principal Investigator Scott Bolton of the Southwest Research Institute in San Antonio, Texas. The mission is part of the New Frontiers program, which is managed by NASA's Marshall Space Flight Center in Huntsville, Alabama. And the spacecraft was built by Lockheed Martin Space Systems in Denver, Colorado. There have been other missions to Jupiter before. There was Pioneer, Galileo, but unlike the others, Juno is solar powered. And as Bill Nye will tell you, as only Bill Nye can, powering a spaceship 500 million miles away from the sun is not easy.
In Roman mythology, which of course is rooted from Greek mythology, Juno was the wife and sister goddess.
All right. Juno project manager Rick Nybakken is with us, and this is a huge day for the team. I have to say my heart stopped at 8:18 right then. Was it the same for you?
Well, it stopped and then restarted.
Hey, there you go.
Just like our main engine.
And I'm sure it was for the entire team. And this is a pretty big team. Just yesterday, the group went to the Rose Bowl. We have some footage to show everyone. You guys took a group photo. Is that right? Oh,
And
look at that.
it was quite a day for us because in a way this was a pre-milestone to today. The team got to celebrate the achievement. It's taken 10 years to get to this point, 5 years to get to launch, and another 5 years to get to Jupiter. So we're really excited to be here.
And that stencil is actual size?
Yes, in fact, that's the first time that we've ever seen the spacecraft full size.
Oh, really?
It's so large that we could never open all the arrays in any of the facilities.
That's
we were
right.
in.
So when you built the solar arrays, you were never able to test them at the same time. You couldn't open them all up because the spacecraft was so big.
That's right. So one by one. So in a way, this is the first time we've ever seen the full-size spacecraft.
It must have been a real kick for the team.
It was.
Oh, and we also have a video that shows a comparison of this spacecraft to other spacecraft. Can we roll that?
Let's take a look. Yeah, so you can see different nuclear-powered spacecraft. There's the Mars Science Lab. And there, of course, is Pluto New Horizons. And then Cassini. These are all nuclear-powered. And we're the first mission to go out to an outer planet that's solar-powered. And you can see the massive size of our arrays, 60 square meters, almost 19,000 solar cells on those arrays.
And the reason being is because of the solar arrays. You need that much space to get the energy that you need?
Yes, we have a very power-efficient spacecraft, but the sunlight's only 1/25th at Jupiter of what we get at Earth. And so we had to take these solar cells and determine how well they perform under low light, low temperature, and radiation conditions, and then we size the arrays appropriately. Those arrays give us over 500 watts of power.
500 watts, 5 light bulbs, 5 100-watt light bulbs.
Just like four lamps in your home.
Wow.
It's very power efficient.
And let's give people an idea of how big it is. I've been told that it would fit into an NBA basketball court.
Well, yes, in one dimension it's much bigger. It's not quite rim to rim, but it is massive. You can get a sense of the scale right there. It's a beautiful vehicle, isn't it?
It is. And we talked a little bit about that, the design of a spinning spacecraft. It spins because it reduces the need for energy, and it's an old design, a relatively old design, a mature design.
Yeah, there's not that many spinning spacecraft out there, but it gives us a lot of stability. It simplifies our operations, and we have a plethora, 8 science instruments on board. And just on the body of the spacecraft alone, we have 18 different sensors looking out to the side. And so the spinning spacecraft helps share all the viewing time. So all the instruments get equal observation time with Jupiter and space.
And that's another thing, the fact that this spacecraft always faces the sun. So it's a polar orbit, but it never stops looking at the sun, except in a case like this when we have to turn away to burn our engines.
That's right. If you're the sun, and this is Jupiter, the spacecraft comes in over the top, and all of its orbits are in this plane, so we never go into Jupiter's shadow. A pretty important requirement for a solar-powered spacecraft.
Right. So we are getting close to the burn. We're partway through. Bring us up to speed. What's happening with the spacecraft right now? We've got some imagery of the burn. What's taking place? Bring us up to speed.
Well, the main engine burn is 35 minutes, and it'll slow us down just enough to go from a super long orbit. We would just fly by Jupiter without this burn, which of course we don't want. After 35 minutes, we'll be in a 53-day orbit, and when the burn completes at 8:53 p.m., we'll immediately start to spin down to 2 RPM and turn back to sun. That'll happen by about 9:30 p.m., and that's obviously really critical for a solar-powered mission.
So right now it's on battery power because it has to turn away from the sun.
That's
so
right.
you want to get back to the sun as soon as you can.
Yeah, this is the only time in the mission where getting to the sun is second priority. The first priority right now is getting into orbit, and it'll keep firing the main engine until we're successful. And right now it looks like the main engine is just doing great.
You mentioned something at the news conference earlier today. You said this is not the first time you've fired that engine. This is the third time.
Yeah, it's a very well-designed mission. We fired the main engine twice, very successfully, back in 2012. And we know how to fire the main engine. It worked perfectly twice, but what's new here is we've never done it in Jupiter's environment. And the first peak of radiation that we expected to see is already past us.
What's
and
the
next
second?
one, it's after the main engine burn.
Okay.
So it's looking really good, but this is exactly how we designed the spacecraft and the sequence to operate.
And that's how it always is with missions. You prepare as much as you possibly can, but there's always that uncertainty when you get there.
That's right. We worry and we fret and we test and we
Right.
go over it again and again and again. And this is probably one of the most thoroughly tested sequences. We started way back in 2011 before we launched. We've thought about every conceivable scenario, but nevertheless, we're really glad to see the main engine burn going so well.
But you just don't know what Jupiter is going to throw you.
It's a really crazy place to go.
Yeah.
I mean, someone who's outside the business would say, are you nuts? Why are you going into the most hazardous places, especially this deep into the radiation belts? But, you know, we spent 5 years before launch thinking about exactly how to make the spacecraft ready to handle that intense environment.
All right, so you'll be holding your breath one more time at the end of the burn?
Yes. But we'll certainly be paying attention.
You
It's going well
and
so
me
far.
both. All right. Thank you so much. Rick Nybakken,
Thank
he
you.
is the project manager for the Juno project. And you're watching live coverage of Juno's arrival at the Jet Propulsion Laboratory. And right now, we are going back to the MSA and rejoining Stuart for an update.
Hi, Gay.
Hi, Stuart.
Hey, Gay. Everything's going really well so far as we can tell. The tones that signaled the start of the burn weren't seen right away, but we did in fact record them, and we verified that we received them at our other DSN complex. So we verified with the tones that we started the burn. More than that, though, we also verified with something called Doppler, the change in the frequency of the radio signal that we're still getting. It's just the regular carrier signal that doesn't have information encoded on it. And we can tell that that signal changed at the moment of the start of the burn and changed in its slope in such a way that the change in velocity was recorded, and we could tell that we're starting to record that change in velocity as we're now slowing ourselves down as we go into Jupiter's orbit in that 35-minute burn. So we're monitoring the Doppler. We also saw the Doppler changes for the turn and for the spin up, and we'll see more Doppler changes a little later that accompany the tones and telling us something about what's going on the spacecraft. Everything looks great so far. We're a little less than halfway through the entire 35-minute burn.
All right. right. Well, the primary goal of this mission is to improve our understanding of Jupiter's formation and evolution. The spacecraft will investigate the planet's origins, interior structure, deep atmosphere, and a magnetosphere. Juno's study of Jupiter will help us understand the history of our solar system and provide new insights into how planetary systems form and develop in our galaxy and beyond.
Gay and others, I think we're about one halfway through the 35-minute burn. We've got another halfway to go, but what that means is that we started the burn on one side of Jupiter's equator, and we're going to end it on the other side of Jupiter's equator. And we're right now roughly crossing the equator of Jupiter at the closest approach point to Jupiter. It's actually 3 degrees north of the equator. And that closest approach point, closer than no other spacecraft has ever been before, is about 2,800 miles above the cloud tops, or 4,500 kilometers. And our velocity, our speed, is 58 kilometers a second. I'll translate that for you. That's 36 miles per second, or about 130,000 miles per hour. That's the fastest we'll be going relative to Jupiter as we go right past at its closest approach point. We'll slow down a little bit as we go past that. We're continuing to slow down in general with our burn, just enough at the end of that 35-minute burn to put us into orbit about Jupiter in the right 53.5-day orbit that Gay was referring to earlier.
Mission names are often acronyms. For instance, MSL means Mars Science Laboratory, or OMG stands for Oceans Melting Greenland. But as Principal Investigator Scott Bolton explains, Juno is named after a goddess who could see through clouds.
In Roman mythology, which of course is rooted from Greek mythology, Juno was the wife and sister goddess of Jupiter, or in Greek it was Zeus, and the Greek name for Juno is Hera. So they were companions, and Zeus, of course, was the king of the gods, and she was the queen of the gods, Juno. She was married and cared a lot about children and marriage and keeping everybody well-behaved and sort of like a good mother would. And Zeus was sort of being naughty with some friends and doing things, and he saw Juno looking down at him or starting to come close to him. So he cast a veil of clouds around himself and his friends and tried to hide his naughtiness. But of course, Juno was a fairly powerful god herself, and she saw enough that she said, okay, I'm suspicious, and kind of traveled down and used her powers to look right through the clouds and see the true nature of Jupiter and understand what he was really up to. And that's exactly what the Juno spacecraft does for us, is that it goes there with special instruments in a special orbit and uses its magical powers to see right through Jupiter's clouds and understand its true nature, which is holding these secrets for us about how the solar system formed and where we all came from.
Scott Bolton, the PI from the Southwest Research Institute, joins us now. This has been your baby. How does it feel to be seeing us go through the burn like this?
It is incredibly exciting. I mean, it's going well. The rocket's burning. We're slowing down and getting into orbit around Jupiter. It's so great of a feeling.
Now, what are you watching out for as we go through this burn? Are there key moments that you're watching?
So there's a couple of milestones that
Okay.
I think are really critical. One of them is the burn, the 20-minute mark on the burn, which we're coming up to really quick.
We're at, 39 minutes past the hour.
We're at it, basically.
We're at it.
And so that's a critical point, because although we're not in the orbit that we really desire, we probably burned enough that we're captured by Jupiter.
It's interesting. We heard the team clapping just a little while ago. So they were clapping at the fact that we are technically, it may not be the orbit that you were hoping for just yet, but we are already in orbit around Jupiter.
Right. Even if the engine stopped right now, I think we would just be in a very large orbit.
Okay.
So we've made the transition from being in orbit around the sun to being in orbit around Jupiter. At least that's the theoretical predictions, but it's right around that 20-minute mark, so we should have just crossed that. Every minute now is icing on the cake. We're getting it better and better into the closer orbit that we want, which improves the science, gets everything that we want. And then there's another critical time, about a half hour after the burn stops, where we actually have to turn the spacecraft back to the sun. That gets us power positive again. Right now we're running batteries, right? We can't get any power because the solar rays are not pointing at the sun. We've got to point that back to the sun so that the juices start flowing through Juno's veins again. That's what gives you the electricity for the rest of the mission.
So for a solar-powered spacecraft, that's your lifeline.
That's it. That's the critical time. You've got to get back on the sun. So we're not out of everything, all the risk, but the majority of the risk we've already accomplished.
Earlier today, the team released a movie, the approach video, and we can run it and show people what you see as Juno comes in. It was taken up to 5 days ago, correct? Because you had to turn off your instruments. But here it is. What do you see when you see that?
So what you're seeing actually is the first time that humans in any time in history have actually been able to see the motion of the heavenly bodies. I mean, this is how nature works. We've never actually been able to see it. This is what Galileo realized.
That was what Galileo saw in the 1600s.
Absolutely. He pointed the first telescope up at the planet. He was clever enough to realize that over a few nights, those stars near Jupiter seemed to change position. And he realized, oh my gosh, that means they're going around Jupiter. And of course that changed our culture forever, because all of a sudden you had, Earth wasn't the center. Here's something else that's got things going around it. That was a very profound moment for our culture. It changed us, our perspective on even ourselves and how we fit into nature. And now, 400, 500 years later almost, we're able to actually see the motion ourselves. This is the first time. We haven't even got a movie of any planet and moon together, and so it's great that Juno was coming in at this angle and had the right kind of camera to capture this motion.
You've described that picture like it was a mini solar system. Is Jupiter kind of like that?
Absolutely. That shows you. Jupiter is really a mini solar system. It has a few moons. Those are the Galilean moons. Mm-hmm. Those are the brightest. You're seeing them go around at different periods. That's natural harmony. And if we back off of our whole solar system, that must be what we would look like. Now, of course, if you did back off and you saw the sun, the easiest planets would be Jupiter, Saturn, Uranus, and Neptune. Earth and its neighbors would be really tiny dots. But that's the way we must look. And if you back off of that, our sun is going around the galaxy. I mean, so the harmony is there in nature at every scale, even if I go down to the atom and the electron going around the nucleus.
Well, let's talk about the camera that took that image, Juno Cam. It has a special significance to you and also the team. Can you talk about that?
Absolutely. That camera is truly an outreach camera. It was designed to be able to get the first picture of Jupiter's poles, and as we fly over, we'll capture that.
There it is.
You can see that in this video right here. That is Juno Cam right there. And Juno Cam is an outreach camera in the sense that you can go onto our websites and you can, the raw data will be loaded up there for the public and schools to actually process themselves and create these images. And they can do more than that. They can actually go on the websites and help vote where we point the camera. So if they've got a special or favorite feature on Jupiter, like the Great Red Spot or some other little storm, they can vote, demonstrate why they think it's important. The public gets a chance to share in that vote, and whoever gets the most votes, that's where we're going to point the camera. And we'll have that up and running a little bit later in the mission. As we go into our prime mission, the public's going to get a chance to join our team and actually get the images and help decide where the camera points.
And what sort of response have you received from schools, from teachers, from students?
Oh, an incredible response. And we were just getting started, and a lot of the amateur astronomy community have jumped on board. Whole schools have jumped on board. We threw out a little experiment as we flew by the Earth a few years ago, and we didn't even have the website up yet, but we put the data out on the web, and while we were sleeping, in the middle of the night, we woke up and all these images of the Earth were already made for us. So it's great to see, citizen science. The public is joining our team, and we need them.
And so they will have access to the actual raw data and be able to do what they will? Will they be able to work with the imagery themselves?
They will. I mean, what we will load on is a little bit less than just raw, because that's a little difficult to deal with, but they will be basically each filter somewhat raw, arranged, and they can mix the colors the way they wish. They can bring out different features by dialing these things up.
And
they
doing what scientists do themselves.
They can process them.
Okay.
They could make a little movie, with taking that sequence.
Just like we just saw. All right. And not only that, we have Juno Cam, but I'm told that you also have some hitchhikers on board this spacecraft. Can you talk about that?
I often get asked, do you have any passengers on board? And we do, but they're Lego minifigures. And we have Galileo on the left side. In the middle is Juno, the goddess. And on the right side is Jupiter with his lightning bolt.
And what are they made of?
They're actually made out of spacecraft-grade aluminum, and they're inside of our spacecraft. They're getting the ride of their life right now, and they've got the best view of any of us.
And why did they decide to have these extra passengers, so to speak?
So it was part of an outreach education program. LEGO's a very educationally minded company, and I wanted to reach out and help children work both creatively and analytically. And of course, when you're building Legos, you're doing both the mathematics and you're creating something new. And so we reached out to the company, and NASA embraced that and created a little bit of a collaboration. And we ended up suggesting if they wanted to fly some figures, they could do that. We helped, kind of jointly designed them. They made them themselves. Of course, I gave them the specs and what kind of metals to use and what to do, and then NASA tested them just to make sure everything was okay, and then we mounted them on the spacecraft, and off they went into space.
All right. Well, we are just a few minutes away from the end of the burn, but what's going through your head? What are you most anxious about, and what are you looking most forward to as part of the science team?
Well, now I'm a little more relaxed than I was before the burn started. But so I'm really looking forward to the science at this point. I'm starting to realize, okay, we're going into orbit. This is going to get started. It's fantastic. And I'm just so curious about the discoveries that we can make and learning about our beginnings and what can Jupiter tell us about how the solar system was made.
And managing expectations, because this was such a critical moment, we turned off all the science instruments right now. When can we expect some science coming back?
A couple of days from now, we'll turn the instruments back on, but our first orbit is 53 days long. And so we come back to Jupiter with all our eyes and ears open the next time, but that's not till the end of August. But we will have spectacular discoveries on that at that time.
All right. Well, I know you want to get back in there, so thanks for joining us.
Thanks for having me.
Good luck to you, and we'll be all holding our breath. All right. Take care, Scott. So it's about 48 minutes past the hour here at NASA's Jet Propulsion Laboratory. We are getting very close to the end of the 35-minute burn. Let's hand it over now to our mission commentators, Stuart Stevens and Tracy Drain in the control rooms at JPL and Lockheed Martin.
Hi, Gay. We're happy to be almost through our burn. You can tell from the Doppler that we're looking at that everything is going smoothly. We're continuing to burn and change our velocity. We've got about 5 minutes or less now at this point before we complete the burn. You heard some minor celebration earlier. You'll hear more when we complete the burn because we burned long enough, roughly 20 minutes or so, so that we are now in an orbit around Jupiter. It's just not quite the right one we want to be in. As we burn more and more, we'll get closer to the right orbit period of 53.5 days that we want to be in. Right now it's a much larger period if we were to stop the burn at this moment. So both the tones, we aren't getting any tones right now, but we will get one at the end, and the Doppler are telling us that everything's working on schedule, and we're just holding our breaths for another 4 minutes or so, both here and at Lockheed Martin with Tracy.
Yep, and you can kind of see if you look behind us at the NSA, the team here at Lockheed Martin, people are standing on their feet. You can feel the anticipation building. It's pretty great that we've been able to see, as Stuart mentioned, that the Doppler is going pretty smoothly. And so the tension level isn't exactly higher because we feel from as much information as we have in hand, things should be going well. We should be captured. But we're all eagerly awaiting the tone that'll tell us that the burn has indeed cut off on Delta V and we're in the exact orbit that we want to be in. So we're all waiting for that to happen.
You can't hear it? Rick, speak for you. That's a YouTube internet sensation right away. Exactly. Is the Bluetooth interfering?
It's okay if I get fired at that point. Everybody's
All right, we are about 30 seconds away from the minimum burn, which was 52 minutes after the hour. And I see a display here, and the estimated orbit at this point is about 62 days, and it keeps counting down. The longer we burn, the shorter the orbital period. At this point, at this stage of the burn, it's about 61 days. So we're just counting down.
All stations on Juno Core, this time we see the tone for minimum burn timer. Almost there.
Yes. Where the orbit here is going to get small. John's going to see it first.
All stations on Juno Accord, we have the tone for burn cutoff on Delta B. Gratito mum Juno. Welcome to Jupiter.
Systems, this is Prop.
Go ahead, Prop.
Based on the from the burn time was 21:02 seconds, only differing 1 second off of the pre-burn predictions.
Copy that.
Welcome to Jupiter.
At this time, we also see the tone for the spin down to 2 RPM started.
We're back on.
Long time coming. Yeah. John? Can't beat that. Can't beat that. Well, at least 1 dB better than I expected. Congratulations to all of us. All of us. We're in it, man. We're in it. Everybody, man, you're the best team ever. We just did the hardest thing NASA's ever done. That's my claim. Well, we got to get sun pointed.
And a big sigh of relief for the team here at JPL and at Lockheed Martin. And right now, NASA Acting Associate Administrator for the Science Mission Directorate, Jeff Yoder, is here. We are officially in orbit around Jupiter. How's it feel?
It feels great. This is phenomenal.
The fact that it's happening on your watch, how does that feel?
You know, with over 100 missions in the Science Mission Directorate, seeing that an event like this just highlights the talent of the NASA, the contractor, and our partnership team to be able to just accomplish an incredible, difficult mission like this. It's just phenomenal.
And the fact that we have accomplished, I mean, we are now in orbit at Jupiter. What does this mean? What sort of pathway does this forge for future missions?
For future missions, this is just one step in a lot of firsts, really, for the Jupiter mission that provides technologies and advances for upcoming other missions. It also will help answer some of the key puzzles and key questions for how our planets are formed.
And what's ahead for the Science Mission Directorate? What's coming up?
So we have a lot. Again, with 100 missions, we have a tremendous amount of opportunities. Coming up this fall, we have another mission called OSIRIS-REx, launches in the September time frame, that will go to an asteroid called Bennu, that will retrieve a sample and return. We also have a mission in partnership with NOAA, our other partners, that will take a mission called GOES-R that will launch later this fall, and another Earth science mission called Cygnus that will launch in the November time frame. It's a constellation of 8 microsats. And then also some instruments that we will launch to the International Space Station, supporting both our Earth science and astrophysics missions. So there's a lot ahead for us.
So you have a full plate.
A very full plate.
All right. Well, congratulations.
Thank you.
And many more successes ahead.
Thank you.
Thanks, Jeff. Well, let's go back to Stuart in Mission Control. You know, yes, we have the burn complete, but this is not the end of the workday for Juno. Can you explain?
Sure. We're really excited to be in orbit now, but now that we've completed the burn, we've started our spin down to 2 RPM. We'll hear a tone shortly for spin down complete, and then we'll start some nutation damping, and eventually do a turn after the end of your broadcast back to sun point. We have to get sun on the arrays, and tomorrow we'll turn back to the Earth and do other activities. But right now we're just glad to be in orbit.
Are officially in orbit at Jupiter. Right now, we are going to introduce you to our new director here at JPL. His name is Dr. Michael Watkins. And Mike has been on the job for a big whopping 4 days now.
Since Friday.
And look, you have a successful mission, not bad.
Yeah, right. It's a good start. But you know, you and I have sat at this table many times, so you know, I worked here for 20 years before last Friday, but the first time as a director, it's a good way to get off to a good start.
And
this
let's
is just
talk
a regular
about
4th of July.
Yeah,
here
a
in
regular.
Pasadena.
We do this all the time.
Absolutely.
But let's talk about that. You have been on missions before. You know what it's like for the team. What is it like to have a success like that after you've worked so hard, years on something?
Well, yeah, it's a combination of excitement and relief, because you know you're overjoyed that it's there, and that the reason you did the mission is now come to fruition. At the same time, you can't help but worry that something can go wrong. So there's a great feeling of relief in addition to that joy that you know that you're there at Jupiter or you're there on Mars. But don't forget that this is the beginning of the science mission, right? So
Right.
in some sense, it's the end of the voyage, but it's really the beginning of the science. So the reason we do these missions is to learn about Jupiter and to get all the great science out of the mission, and that's really what's just now starting for the Juno team.
All right, and there's still much more to do, and we've just heard over the VOCA that the spin down is completed. There's still a little bit more work to be done with this spacecraft. It still has
That's
to do
right.
a few more things, right?
Has to get itself oriented back, you know, pointed at the Earth, get the solar rays pointed at the sun, and you know, get back in communication with us, get itself back in kind of a nominal mode. And when it does that, then we'll know that we're in perfect shape to initiate the science mission.
So when will you be a little bit more comfortable? When it's back on Earth point or when it's back on sun point?
Yeah, in just shortly, like another hour or so later tonight, we'll know that everything's back in good shape.
But it's looking good so far.
Oh, it looks perfect. It looks great.
All
Absolutely
right.
great.
All right. Well, thank you and welcome. Nice start, Director.
Thanks very much. Welcome to Jupiter.
Welcome to Jupiter. The spacecraft is turning to the sun, and we'll swap back to the medium gain antenna. At about 9:07, 9:11 p.m. our time. It should be back on sun and off battery power by about 9:30 p.m. Pacific time. Our thanks to Stuart Stevens and Tracy Drain for explaining this very complicated engineering and teamwork that has to take place in an event like this. We're going to wrap things up here in Mission Control. Coming up next, the post-JOI news briefing is at 10 p.m. Pacific time, 1 a.m. Eastern time. And for more information on the Juno mission, go to www.nasa.gov/Juno. So there you have it. The mission joins a lineup of NASA successes on the 4th of July. There was Mars Pathfinder in 1997, the Deep Impact mission at Comet Tempel 1 in 2005, and now